It's fine, right? Video is not required. Very. We don't need a mic. Probably he might want that. Yeah.
I don't think the mic on that.
We'll go to that side.
And I believe you can actually turn this, and then it will fall a little bit lower. Is that too low?
I think that's
good.
fine.
Okay.
Anyways, have to be close to.
So it's on.
Okay. All right.
Yeah, hello everyone. My name is Prashant. I am part of the OWASP various chapter. So welcome everybody. First of all, thank you very much to City College for hosting us. Thank you, Gary and Ram and professors here. It's really nice that you guys are supporting OWASP in a big way. Welcome all. I would like to introduce Asim Jadar, who is founder of one of the great conferences in India called Nalkwan. Also a founder of a company called Payatu. They do a lot of work on mobile application security and exploit writing and IoT security. So Asim to start over now. So Asim, up to you.
All right. All right. Good evening, everyone. Am I audible at the back? Yeah. All right. I have to stay near the computer for the video, so. All right. So I'm going to talk about an open source framework that I've been working on, and I've released this on GitLab as well. I call it Exploitation. It's not exploit. It's IoT. I always have problem with the word here, but yeah. Right. I think he's already explained a little bit about me. We actually organized two conferences, one called Nalkwan in Goa, India, and one called Hardware.io that focuses only on hardware security, and that's an annual conference held in the Netherlands. Apart from that, I mostly work on research on IoT security, and this is one of the outcomes of our research. And yeah, so I'm going to talk about the framework and how you can use it, and what are the benefits. And at the end, I would like some feedback from you on how I can improve the framework. I also do a training called Practical IoT Hacking at most of the security conferences. All right, so I'm going to talk about what are the security issues. How many of you have worked or are working in IoT? All right, mobile. Okay, cloud. All right, hardware. All right, so just that piece is missing then. Okay. All right, so I'm going to talk about what are the challenges with IoT and what is the attack surface of IoT, and then focus more towards how we're trying to solve the problem. All right, so the state of IoT security, well, it's not good, but it's you can relate it to the state software security was back in the 90s. Hardware has become really cheap. You can find development platforms and create, if you have an innovative idea, like a toothbrush that connects to the internet and just monitors the state of your teeth or whatever, connected spoon, connected forks, whatever you can think of. The good thing is the hardware is cheap, so now you really don't need too much of a funding. If you really have a good idea, you can go ahead and buy any cheap development platform and prototype your product, which is good for innovation, but it brings with it a lot of challenges from a security standpoint. So some of the apparent problems are that when startups come up with new ideas, they source the hardware or the platforms. So those companies are not necessarily hardware companies. So they do not understand the nitty-gritties, and they tend to trust the hardware of the sensors that they're using. The other problem is funding. So some of the startups do not have enough funding, and since there are too many companies now jumping into the IoT industry, everyone wants to reach the customer first, and this is where the problem starts. So what happens is the companies would let go of certain processes within their secure software development lifecycle, and one of the most common process to let go of is security testing. I mean, we've seen companies even let go of functional testing. So you would just quickly develop the product, do a little bit of unit testing, and start shipping the product. And the whole idea is then we can fix the bugs in the later version. But the problem is you can fix some of the software bugs, but if your hardware has security issues, loopholes, there's no way in which you can fix other than recalling the hardware back. And some of the products are really cheap, so recalling also doesn't make sense. People just throw it. The other issue is that when you start developing, people are really not sure which protocols to use when it comes to IoT. So there are protocols and standards available, but then when you really need to quickly release the product, then you look at the learning curve and the implementation time for any protocol, and some of the companies really get confused on which protocol to use. So either they would use a protocol which is famous for some reason or the other, and try to fit them in their ecosystem. Actually, it should be the other way around. Or some would say, let's chuck the protocol. Our sensors are really just sending, small values. They're just sending float values. Why not we just use, normal UDP-based communication, for example, and we would just create a simple format in which we can exchange information. But we will keep it secure because we are going to use encryption. And that's another challenge. You may use encryption, but it's not only about using encryption. It's about how you use and how you implement the encryption. So you may have AES encryption 256-bit, but it doesn't matter if somebody can get access to the keys, for example. All right. So from the attack surface perspective, so when somebody sells you an IoT product, he's not just selling you a product or one device. You actually get access to the whole ecosystem. So you have a mobile app for user interface. You have the cloud, which stores all your personal data, and then you have the sensor or the hardware, which does the physical world interfacing. So from a very high level overview of the IoT ecosystem, I see three major attack surfaces. Obviously, one is the mobile itself, one is the cloud, and one is the hardware. Now, cloud is a very critical aspect here because of the way the whole architecture. There's no set architecture for IoT. Companies may come up with their own architecture and show you complex diagrams. I think just don't pay any importance to that. It's all about connecting the components of the IoT ecosystem in the most efficient way possible. Then based on that, there are certain standard ways in which you can have your ecosystem. For example, if you really need your sensors to be remotely controlled, then you would have an architecture where the user may not directly communicate with the sensor, but the cloud would play a central role where all the information would pass through the cloud, and the cloud will control all the deployed sensors around the world. Now, you may try and research on a particular product, and you may find loopholes where you can access that product. But think of the loopholes in the cloud. Since the cloud is only one instance that is going to communicate with all the deployed products around the world. You access cloud and you get access to all the deployed products. But thankfully enough, OWASP is doing really a good job in providing guidelines and standards. OWASP Web Top 10, for example, Mobile Top 10, for an instance, and then there are a lot of other institutions which are which have published guidelines on cloud security as well. The challenge that we see is that nobody is talking about hardware security. And even if companies or organizations are talking about hardware security, they are really restricting it to their own domain. For example, automobiles will focus on, automobile industry will focus more from the automobile perspective. Healthcare would focus more from the healthcare perspective. But if you really look at the hardware at a very low level, I mean, the problems are common. So they're not industry specific. So given a specific hardware, you would use standard techniques to bypass the hardware security, get information about the logic of the product. All right, so this is when we started looking at IoT security, and we got a few projects, and we were like, we know security, and we can beat the shit out of any product given to us in our lab. So we were very happy because we were doing something different, and we thought that the same rules or the same process would apply to anything, right? Turns out when we started testing, this is what happened. I mean, we started to look for different hardware tools available. We had to purchase different hardware. We had to look at different tools or libraries available which would allow us to implement or interface with the IoT protocols. And we figured out that most of them are not mature enough. And we basically ended up writing our own custom scripts to do communication and analysis of the whole ecosystem. Yeah, so the problem was there are just too many interfaces, and no two consecutive tests that we have done have too much in common. So it will typically depend on the use case of the product. So for example, we were doing toothbrush, and then suddenly the next test that we are doing is an AI-based vacuum cleaner, which has nothing in common. And then the next thing that we are doing is a food processing machine. So our tools change, everything changes. So that's when we sat down and we thought, what can be done to make this process more efficient, so that we really don't have to invest, or anybody who starts testing really does not have to invest too much time, or I should say waste too much time in looking for different tools or creating their own custom tools to do security assessment for IoT. So we've been I've worked on a lot of open source. I've released an app called Diva Android. Basically, that's an app where you can play around and learn Android security if you're interested. Just search for Diva Android. Diva is short for Damn Insecure and Vulnerable Application for Android. And then since I do the practical IoT hacking training, we've also come up with a hardware board called Diva IoT, which demonstrates standard hardware security issues, which I use to teach students what you need to look at when you're analyzing the hardware of an IoT device. And that's when we came up with the idea of Exploitation. So the design goals and motivations were that it has to be simple to use. So anybody who wants to get into IoT security or has a product that he wants to test, it should be fairly easy for that person to automate part of the test and spend more time on reverse engineering and analyzing communication as well as the firmware. The other goal was that it should be extendable. So it should not work as a tool. For example, if you are a penetration tester, or if you are a manufacturer of an IoT product, and you need to have a security regression test suite. Right now, if you were to do that, you're going to waste at least an year writing a regression test suite, and that will be only specific to your own single line of products. So so that was one of the goals, that we provide the basic framework and anybody can go ahead and extend it. All they need to do is just use the plugins and the protocols available in the framework itself. So the architecture right now is pretty simple. Actually, the framework itself right now is basic and simple. So the heart of the framework is the protocols. So we are focusing on IoT protocols which work on TCP/IP networks, radio-based protocols, because there are now different tools to do analysis for different radio protocols. For some of the radio protocols, there are still no tools available for researchers to use. So that's the bridge that we want to. That's the gap that we want to bridge. And the next is hardware interfacing. Now, how would you go about interfacing with the hardware to analyze or find out hardware security issues? So if you want to extend it, all you need to do is just write your own plugin. All you need to do is just extend or inherit from test case class and provide basic information about the plugin, like your name, email address, what is the product that it is targeting, is there any reference for this particular exploit or plugin. And then all you need to do is just implement three functions: pre, post, and execute. Pre and post are optional functions if you have any setup or tear down that you want to do within your plugin, or if you have any dependencies. The only function, or basically the only thing that you have to implement, is the execute function, and all of the functionality for communication and analysis is provided within the protocols library or the protocols package. And you can use whichever protocol or whichever utility you want to use and implement your own plugin. All right. So current plugins, we have few plugins that we have already implemented. Some of them are really, really useful. So, for example, for MQTT, we have publish and subscribe. I'll come to MQTT or most of the plugins in detail a little later. We have an authentication brute force for MQTT protocol present as well. For Modbus, we have read-write plugins that will allow you to read coils and register values on a PLC or a Modbus server and write values as well. We have read and write for CAN bus. So if you have a CAN network, you can hook on your PC to the CAN network and start reading and even writing to the CAN network itself. We have some interesting plugins for BLE. Most of the IoT devices or sensors now use a protocol called BLE, or Bluetooth Low Energy, which is more targeted towards low power devices. So most of the protocols in IoT are more geared or targeted towards low power devices. Protocols like BLE, Zigbee, COPE, all of them have reduced, or all of them are simple protocols where they just exchange simple information to make the battery life of the sensor longer. So we have with the BLE, you can scan your vicinity for BLE devices. You can scan for more information about the devices. You can read and write values to the BLE sensors. You can even fuzz test the BLE devices itself. So I will go on to details of each of the modules and the protocols, which will give you more idea of what you can do with the framework. And then I've recently implemented an SPI Flash read-write plugin. right now it's using a Python library which is limited to 7 or 8 different types of serial flash chips. But going forward, we're going to integrate more open source libraries, so we can have a wide range of chips supported. So basically what this does is, provided an address, it can go ahead and read data from the flash chip. And you can also dump data from the flash chip, and you can write data back to the flash chip itself. And there are standard there. We've also started manufacturing multi-protocol connectors, which you can use to connect with the flash chip and connect it to your PC, so that you can basically read write the memory chips. So typically you would want to do that mostly for reverse engineering the data that is stored on the device itself. When we talk about flash chips, mostly they would store the firmware of the device. But if not firmware, then it would be the user data or the sensor data itself. I have a couple of plugins implemented, exploits implemented. One of them is basically a POC to control. So Cancun is a Chinese smart plug, and because of the way they implemented encryption, the key was hard coded. So we have the key now, so you can basically control. If you are on the same network that the smart plug is, you can switch it on and switch it off without any kind of authentication. And then there is another company called TapLock, which makes smart locks. I think this was on Kickstarter. And so this smart lock works in two ways. Either you can unlock it using your mobile app, or you can also save your fingerprint information on the lock. So the way they implemented the unlock functionality, again, was not based on pure authentication between the mobile app and the lock. So now there is a researcher from UK called Cyber Gibbons. He figured out by reverse engineering just the mobile app on how what information is the mobile app sending to unlock, and it turns out it has nothing to do with user authentication. So we have that plugin implemented as well. All it does is it'll scan for the tap locks in the vicinity and send them unlock commands. And then there is a plugin called Serial Brute Force, which is an interesting plugin. So in our tests, we generally found that even from the embedded devices, not just IoT devices like IoT sensors, typically would have some kind of a serial console which is exposed on the hardware itself. And these serial consoles are usually used by the support staff to troubleshoot or debug any kind of problems on the hardware. Once you connect to it, usually it may either give you a shell, root shell in most cases, or if the vendor has implemented their own custom console, it will give you a custom console. If it gives you a custom console, chances are that some of the commands are published by the vendors themselves, and the vendors may choose to have hidden commands which are not published anywhere. And these hidden commands are privileged commands where you can change the configuration or state of the devices, or get more sensitive information about either the ecosystem or the device itself. Now the purpose could be either for troubleshooting or keeping backdoors or whatever. So we found that so what we did was we created a brute force plugin that just sends random strings to the serial console and just tries to parse the response. And based on that, you can figure out whether there is any hidden command implemented in the serial console or not. All right, so this is the current hardware that we have created. One on the left hand side, you see we call it Exploitation Nano. This is a multi-protocol connector. This uses a chip called FTDI, which is what implements all the enables all the communication. Now, all these protocols that you see, JTAG, SWD, these are debug protocols that you can use to debug the microcontroller directly. And then you have other communication protocols like UART, which is used for serial communication between two components, or the exposed serial console port, as I mentioned, which is present on some of the hardware devices. And then you have I2C and SPI protocols, which is again used for communication between two different components. So most of the flash chips or memory chips would implement either SPI protocol or I2C protocol to communicate. And this is all you need to connect with the memory chip, and then you can use either Exploitation, or there are some other tools available which would read and dump the data from the memory chip. And this is the board that we have created. So this basically has an ARM microcontroller and a ZigBee chip, and basically demonstrates hardware security issues. And so it has an exposed JTAG port, it has an exposed UART port, it does communication with the two memory chips that you see here using different protocols. And we have certain challenges within the board, so you can just plug it into your PC, use any hyper terminal to access the console of the device and start playing with the challenges that are listed on the device. All right, and so right now it is limited to all the TCP/IP based protocols plus one radio based protocol, which is BLE. In the future, that's what we are aiming to have support for ZigBee and other important or famous radio protocols. We're also looking for support for debug protocols and other protocols. So right now we have support for at least SPI, so that we can at least dump data from memory chips, and then more on firmware analysis, test cases, and exploits. Whatever exploits we can find in the wild, somebody publishes on the internet, we will try and port those exploits onto the framework itself. Right now, I have not thought of implementing more of cloud-based plugins or mobile-based plugins, because there are a lot of tools already available which would, which you can use to do cloud testing or mobile testing. So I'm focusing more on areas which are not touched by security folks as of now, where we also face a lot of problems in analysis. All right, so I'll quickly go ahead and show you a couple of a few videos, and then we can go ahead and discuss more about any specific protocol that you're interested in. All right, just wait, where is you can note down the URL here. That's the URL where the framework is. And if you're interested, all you need to do is just git clone the project. The README defines what are the dependencies. It's pretty simple to install. We've tested it on Ubuntu 16 and Kali. It works pretty well. It's not supported on Mac and Windows. So the basic reason is some of the Python packages that we use are only for Ubuntu. And really, I don't see a reason why I should support Windows or Mac. All right, let's go ahead and look at some of the videos. So let's start with the BLE plugins. Oops. All right, so once you install it, you can run directly the utility called EF console. and it implements two commands. One is the list, which will give you a list of all the plugins that are present in the framework. And then if you want to run a specific plugin, you can use the run command. If you want to read more about want to get more information about a plugin, just give -h and it will give you details and the options available for each plugin. So I've tried to keep it as simple as possible. So for example, let's say you want to scan for BLE devices for 2 seconds, you can use this command. If you want more information about the BLE devices which are present, you can use verbose mode to get more details about the BLE devices that you're scanning. Once you get a device, you can get further information about the characteristics. So basically the way BLE works is it uses a protocol called GATT, or attribute profile, and this is exposed by the peripheral devices. So if you see, we are scanning for characteristics here, and you would see some UUIDs. So these UUIDs, some of the UUIDs are defined by the BLE specification for a specific work, and then vendors can create their own custom UUIDs. So you can identify a UUID, a characteristic by UUID, or you can also specify the handle, as you can see on the right hand side. The way you would exchange information with the BLE devices, you would either write a value to the characteristic, or you would read a value from a characteristic. Let's say if you have a heart rate sensor which works over BLE, so you would use the heart rate characteristic handle to read the heart rate from the BLE sensor. And if there is an operation where you want to write, for example, I have a watch here. So let's say I want to set time on this watch, which we will see in one of the examples now. I would write to a specific characteristic, a specific value, which would change the time on the BLE watch. So this is the first one that you see is a characteristic defined by the BLE specification, which is supposed to be the name, or which specifies the name of the BLE device. And then you can go ahead and write to a characteristic value. So typically when you are testing or analyzing a BLE sensor, you would look at the mobile app. You would start, so Android provides you an functionality where you can sniff and store the BLE communication on the Android device itself from developer options. And once you do that, you can trigger an action, save the sniff data, and then open that file in Wireshark, and you can clearly look at what command or which characteristic value was read and which characteristic value was written. So then you can go ahead and use the same characteristic to write different values and analyze the behavior of the device. Now, the other thing here is that the value that you write is not defined by the specification. The value is defined by the vendor themselves, so the developers. And these values are custom values, and the application code running on the device. So when I say the application code, the firmware part that is developed by the manufacturer, that is responsible for parsing the value and then making sense of it. And this is where you would start attacking the device itself. So for that, you have a plugin called BLE Car Fuzz, where you can specify a value that you want to fuzz. Whichever value you want to fuzz, or whichever byte you want to fuzz, you can replace that with XX, and you would specify how many iterations you want to run the fuzzer for. And it will go ahead and start sending random values to the device. We've managed to find a few memory corruption issues using the fuzzer. So typically, as soon as the device crashes, you would get a BLE exception here. or if it doesn't, then you will not get anything. So basically, you keep the sensor in front of you, start running the fuzzers for different characteristics, and then monitor the behavior. Does it go into? So we've had crashes. We've had devices go into firmware update DFU mode, which is direct firmware update mode, and they will start behaving weirdly. All right. Let's come to MQTT plugin here. So before I start, I'll just give you a brief of what exactly is MQTT. So MQTT is short for Message Queuing Telemetry Transport Protocol. It has been used in Facebook Messenger as well. I don't know if it is currently being used in Facebook Messenger. And it is being used by AWS IoT suite as well. So it is quite popular. The way it works is, how many of you worked on or use IRC? All right. So typically it works like IRC, where you have a channel and you join the channel and you can publish messages on the channel, and whoever has joined the channel will see the messages that you are typing. So the architecture is pretty similar. It's a publish and subscribe mechanism. So you have a broker in the middle, which is called the MQTT broker, and the nodes can connect to the broker, and then they can subscribe to something called as topics. These topics are application defined or vendor defined, and nodes can publish to these topics. So for example, if you have a temperature sensor, it will typically publish to a specific topic, and whoever is interested in knowing the temperature of a particular room can subscribe to the same topic. So typically that's how you would the sensor would communicate with the cloud as well. For example, the sensor will publish on this topic, and the either the cloud or the mobile app will pick the temperature by subscribing to that specific topic. All right, so MQTT also provides authentication, for example, and this plugin basically just tries to brute force the credentials and to just test whether the supplied password works or not. So if you get information about the username but you don't know the password, you can try and just do a brute force, or just try and specify a password dictionary which you can download from Google anything, and then start the authentication cracker. So here I'm running a local server which has two users, as you've already seen, USR and USR1, and obviously I know what the password is. So here you can specify a username and a password to test if the username and password is correct. Or if you have information only on the user, then you can specify a password dictionary file, and it will try and authenticate with each of the passwords. So kind of like a standard password authentication brute forcer, but specific to IoT protocol. Yeah. So then you can go ahead, and I have a password file, password dictionary here, a pretty simple dictionary. That's the one. And it will try each password with the user to see if it can find any valid password, for example. Now this becomes very handy because none of the standard authentication cracking tools implement MQTT authentication. So All right, so the next video I'm going to just show you based on MQTT. So the video would demonstrate the capabilities of publish and subscribe through the framework. But what I'll show in the video is irrespective of the protocol. So the idea here is that, or what I think is that in the future, in the coming future, we are going to see a lot of attacks that will focus, or that we will see from the sensor networks coming towards the cloud. The problem is the sensor network right now is assumed to be controlled and trusted, which is where the problem is going to start. And so if you get access to the sensor network itself, you can pretend to be a valid sensor and then start sending information back to the cloud. Now the cloud would accept expect the information in a certain format, and will, if the cloud will trust, or if the cloud trusts the information coming from the sensor network, it may not filter the information. And then based on how the information is being used at the application or at the cloud level, which you can figure out if you are analyzing and if you have access to where the information is going in the cloud, you can, instead of sending telemetry data, you can send standard web attacks from the sensor network itself. This is regardless of how the sensor is going to communicate with the cloud. In this example, I show an example of MQTT, where there is a broker, and then the cloud picks up the information from the broker. There are radio protocols where the sensors would send information to an IoT gateway over radio channel, and then the gateway would translate that and send it over to the cloud. So it really does not matter how the information travels. What matters is what information or what data is traveling from the sensor to the cloud. So here I have again a local instance of an open source MQTT server called Mosquito, which is pretty famous. And I have two plugins here called MQTT Publish to publish data on an MQTT broker, and MQTT Sub to subscribe on a specific topic on an MQTT broker. So here the assumption is that there is an engine room where there is a temperature sensor, and the temperature sensor is sending the temperature data to a topic called temp, and the cloud is picking up the temperature value by subscribing to the topic temp, and then showing the current temperature back to the administrator, whoever is managing the engine room. It's a very simple PHP script that I've written, but the idea is what is more important here, which is what I'm demonstrating, that if you trust the data from sensor network, you may get malicious data, which can attack the cloud or the end user. So here, for example, now I'm sending 23 degrees, and the cloud gets the value, the temperature value, and it displays that to the user. Now, since I am now analyzing the app, now I can quickly figure out that, okay, the data is being reflected, which means that I can now try and trigger browser-based attacks, or send a standard cross-site scripting attack, which would, instead of showing data, may attack the browser again if it's not being filtered. So here I send it, and I get an alert, which is what I had sent from the MQTT node. Now again, let's assume that the information that you are sending is going into a SQL server. You can pretty much try and see if you can do an SQL injection, assuming again that the cloud part is vulnerable to, or is not filtering the user input for SQL injection type data. All right, this one is just pretty simple. So I have a Modbus emulator here called Modbus PAL. So typically Modbus will have around 65535 registers, 65535 coils. So coils will store your Boolean values, and registers would store integer values. So you can basically try and read, if there is no authentication, try and read values from a PLC, and also try and write values back to the PLC here. That's what this plugin demonstrates. All right, so I am writing to coil at address 0. So I'm writing to the first 4 coils on the Modbus server, and then we can go ahead and look that the values have been changed. And we can do the same thing for registers as well. Let me just forward this. So now I'm going to write the value 6 or value. All right, I'm just using coils right now. Let's see if we go ahead and write. Yeah, so I wrote 5 to the first 4 registers, holding registers on the server. Right, we're done with this. All right, so this is the serial brute force plugin that I was talking about. So this is the console for the Diva board, and typically you would have similar console if you don't get a shell on the device, and then you would have a limited set of commands that you can run on the console. So here, for example, if I type anything, sorry, let's go ahead and see here. Yeah, so once you get access to, so typically in your test, what you do is first identify which is the port that is exposed on the hardware. So if you look here in this image, you see these are soldered by us right now, but typically you would see the either pin holes or just copper circles. So those are the test points that are usually connected to the microcontroller. So if there is connectivity to, so there are different ways in which you can test for serial or UART ports that are connected with the microcontroller. Even JTAG ports or other debug ports which are connected to the microcontroller. So here, if you see, I'm connecting to some of the ports, and then we just use standard connector, UART connector, and then we go ahead and use standard hyperterminal utilities like screen, minicom, putty, teraterm, just to access the serial port of the PC or of the device. And if they implement a certain console or a shell and you know the baud rate, you can connect to that. Once you connect to that, then you can figure out whether you're actually getting a serial console or not. In this case, we get a serial console, we type something, we get a response which says invalid input. So now I know that if I give a random string, the response is invalid input. And this is what becomes the basis of me now brute forcing the serial console and trying to figure out if I get a different response if I send a different kind of a string. So here the valid commands are .l, .h, .c, .p, and .x, and from 1 to 7 numbers. Anything else, I get invalid input as the response. So I now go back, run the framework, use the serial brute plugin. It has a lot of options, but it's actually pretty simple. You specify where is the device file of the particular device that you've connected, and what is the character set that you want to use to generate random strings which you want to send to the device. So when I say character set, I mean small a to small z, capital A to capital Z, 0 to 9 special characters. What is it that you want to use to describe your strings? And typically for commands, they would use A to Z most likely, and you may not have commands with numbers, and obviously 99% of the times commands will not contain special characters other than hyphen. So here you define your character set, then you define the length of the generated strings, and then you define a prefix, a standard static prefix that you want to use before the string, and a postfix or an append. The prefix and and the append usually help when you're trying to fuzz test parameters to a command. So you already know a command, and then there is a parameter to that command. You can start and try to fuzz test the parameters of the command, and then you specify a match and a no match criteria. So basically, what they mean is that if you specify a string in match criteria and that string is seen in the response, it will be taken as success. That's the opposite for no match. If you specify a no match string and you see that string, it means it's a failure. So move on to the next string. And then you have basically just serial communication parameters like timeout while reading data or writing data, and buffer size that you want to read from the device, and verbose output. So it will show you the response for each string that you generate and send to the serial console. So here I specify the device file, which is TTY ACM0 in our case, the baud rate that the device works on. So UART protocol is short for Universal Asynchronous Receiver and Transmit. The asynchronous here means that there is no synchronization between the two components. Typically, in hardware communication, the clock provides the synchronization for communication. But if there is no clock, then the two ends have to decide on a speed or bit rate. And this is what the baud rate for UART protocol is, which has to be known by both the ends when they start communicating. If you specify a different baud rate, then you would get gibberish data. And there are ways in which you can scan for baud rate of a serial device as well. So here I'm specifying 4 characters here and a prefix called C, and my no match criteria is invalid, because by testing I know that for a wrong command or a wrong string, I would get the response invalid. So till the time I keep seeing invalid, it means that that is not a valid command. So not useful to me. Now it will start sending 4-character strings and start analyzing the response. And the moment it figures out or finds a response which is different from, or which does not contain the string invalid, it could be that it is a command which is not listed, or basically a hidden command. And then I can use this particular string and go ahead and basically access the device again and test whether that command was correct. or whether there was some other issue. So here I still get invalid for help because help is not a valid command. And chpw, for example, is a command here. All right, and then we have the SPI flash read write. So as I mentioned, these flash chips will typically contain the firmware for an embedded device. And in this case, I'm using a flash chip called WinBond. The manufacturer is WinBond. This is an 8 MB flash chip, and you can connect it using any standard connector that speaks SPI protocol and gives you USB interface. So in this case, I've already connected the WinBond chip to my PC, and then it found the chip, and I specified that I want to read 10 bytes of data starting at address 0, and it was able to read the bytes, and it shows me the bytes. So I can specify arbitrary addresses to read from, or I can say, okay, dump the whole data, whole 8 MB data of the chip into a file if I want to analyze or reverse engineer the data. And that's again pretty simple. You just specify that you want to write, you want to just read everything into a file. All right. So in this case, sorry, this is the SPI flash write command first, where I specify that I want to write from the address 0, and I want to write the bytes 11 hex bytes 11223344. Now I'll go ahead and read the data back just to make sure that the data is written onto the flash chip. All right. The next is I'm going to dump it directly to a file, and then there are again really good open source tools available that will extract the firmware file for you. So there is one tool called Binwalk, which will analyze the binary file and try to see if it contains a file system, if it contains a compression mechanism or file system, which kind of file system, and then extract the file system for us. So here I've dumped it to a file called firmware.bin, and then I can go ahead and run binwalk on it to see what are the contents of firmware.bin, whether it's an actual firmware or whether it's just a data file, which means binwalk is not able to understand. So in this case, yeah, for example, it's able to understand and tell me where the compressed data is, or what are the files present in the right. So the last video, I think this is the tab lock. And yeah. Okay, it goes ahead, scans for the locks present, and sends them unlock command. I think the vendors fixed it. I'm not sure on the current status. Yeah, I think that's about it. So if you have any questions, we can take that questions, or if you have your PCs, you can just download and install this tool or framework. Any questions? Any questions out of the framework or the discussions that we had? Which hardware? This one, yeah. So we are going to start a portal. It's not up yet, but the portal is exploity.io, expliot.io. Where we are going to publish all the information about the framework and the products that we manufacture. So right now we just have two of these products, the vulnerable board. So probably end of this month or next month. We were supposed to launch it in June, but it just keeps getting delayed. But hopefully by this month end or next month, we should start selling this. The Diva IoT board, I don't know, but this, where is it? The Nano, or what we call it, this is basically an FPDI chip, and there are, I think, there are companies which produce similar products using FPDI chip. But we specifically needed it for our tests as well and for the training. So instead of buying third-party products, we thought, hey, why not just make our own and sell that as well. So we are coming up with another version, the next version of this, that will have scanning capabilities on the hardware. For example, if you've been working on IoT or hardware testing, you would know there is a product called JTagulator, which basically scans, given the ports here that you see, you can connect all these ports to the scanner or JTagulator, and it will scan all these ports and tell you which pin is, or which pins are part of the JTag protocol or connected directly to the microcontroller. So we are coming up with the protocol scanning, JTag protocol scanning part as well in the next version of this product. Yes. What? Vendors? Two reasons. One is they're not aware of it. And the second reason is they are restricted because they need to have JTAG ports exposed. So we had one client, and during our pen tests, we showed them that the JTAG port is exposed and it is enabled. So there are two things: exposed port and enabled. Or there are certain restrictions that you can put on the protocol as well. But the problem that they mentioned was that once the device is manufactured, it goes to a third-party company which does post-production tests on the devices. And for that reason, they cannot, because they have a requirement where they use JTAG ports to test, do their post-production testing. That was 2 years ago, and then this year there's a community around the particular product that the client makes, basically a modding community or hardware community, and somebody published part of the firmware of their device, and then we were called back. So they asked us to figure out if there is any, what are the different ways in which the firmware was available, and is there any way. So only part of the firmware was published by the person, and the problem was that they had keys hard coded within the kernel itself, and the kernel was not part of what was exposed by whoever exposed it. Then we figured out that with the JTAG, we didn't go ahead with the JTAG tests in the first test that we did, because they mentioned that let it be, we have to keep it. So this time we went ahead and we extracted the kernel code as well, and we were able to present them with their keys as well. So now they've changing the design, and now they're going to disable the JTAG ports on the new products that they're coming up with, because for them keys are more important, because that is what they use to encrypt some of the files which they consider as PI.
Because JTAG is for like testing. So like instead of like disabling it, like should it allow like authenticate it?
Yeah, I'm not sure if there is any authentication, but you can restrict what you can do with the JTAG protocol. So originally it was designed for testing the pins or the hardware components, but it is so powerful that you can basically debug the whole microcontroller. So you get access to the microcontroller code that is running, the registers in the microcontroller. You get access to the flash within the microcontroller, so you can extract data. You can write data back to the microcontroller as well. So at runtime, you can control the peripherals of the device. You can control what data is stored on the device itself.
Like if I think like from a remediation perspective, if the vendor installs the secure element, some authentication data maybe public
Yes.
insert, and pretty much when you're testing internally to provide authentication details in terms of private data, hey, I'm an authorized party, I'm in this chip. And so only you are allowed to
Yes.
basically
Yes. Yes. I'm not sure if there is any functionality. I've not read the protocol specification, but if there is, I think then we already have a solution. So there was one other chip that had restricted access. For example, this was an interesting vulnerability where they restricted controlling the or read access to the internal flash, for example, but they did not restrict they did not restrict the debugging aspect of the microcontroller. So all the attacker needed to do was that change the instructions to start reading from a specific address till the end where the firmware is present. So even though you cannot read directly or read or dump the contents of the flash, but through the code, you can still go ahead and start reading 4 bytes in a single instruction, starting from where the firmware starts till where the firmware ends. Questions? Nobody leaves the room unless you ask a question. Yeah. If it's running Linux OS, you would have standard file systems like SquashFS, JFS, or YAFS too. But if it's like small sensor, like in case of this, then you would just typically have bare bone firmware. That's everything. And so that firmware is directly mapped onto the flash memory. So that's just code and data. There's no file system, no nothing. Yes.
For folks who are just starting out in IoT, are there any particular devices that you would recommend as good starting points?
I just randomly started buying stuff from AliExpress, and I think you can look at some of the home automation devices or companies which are not very famous. I mean,
So white label stuff.
yeah. Pretty much cameras as well. A lot of smart cameras. Just break it open and see if you can. I'm pretty sure you would be able to find bugs. All righty then. Nobody leaves the room except you two. All right, thank you so much. Yeah.
Wait, can I borrow this? Yeah. So wait. So